Okay, the other one's still taking its time completing, so I'll decide to continue on. Now, as I was trying to say, in C you would do something like this if you wanted to add one structure to another. And if you wanted to add more and more structs, you just declare them inside this struct like a collection. So you could think of A here as a collection of B and a short. I could have another struct called C, let's say. And that one maybe has one of our strings. And let's say that this one also has a, I don't know, something recognizable. A character array. No, we already got characters. And how about, I don't know why I'm thinking about this. It doesn't matter. An integer array. Int r of 12. Okay. And so I could similarly, if I wanted to, have a C in my A struct, which is the same as class. Okay, so now I'm collecting these various things. As you saw in that picture before, the layout of this A struct is just dependent on the ordering and the way that I declare the members inside. Now in C++, there's a way to cut out this naming part. Let's take away C for a minute. And suppose I want A here to have this B member, but I don't want to give it a name. So all I need to do there is put a B like this, a colon and then a B. You can put a keyword in front of here. For instance, as you can with your own members, you can put public and private. Like that. There's a way to specify that when you add a new member through this interface, and you just put the keyword here. So if I wanted to be the implicit member of my structure to be private, I could say private. And that way, if I had an A object here, and I wanted to use this B part, I couldn't. But since we're dealing with structs, and I want everything public, I don't need to specify anything. So now, A here should have the same layout exactly as before. Unfortunately, I deleted it. Maybe I can get it back. Okay, but anyway, it was like this. Yeah. I want a plus and then minus. So we had 6 doubles. 3, 4, 5, 6. A short. And 6 wasted bytes. Let's call it filler. That's an alignment thing. And remember, just as with, I spoke about memcopy and all that stuff before, how it's more efficient to copy things that are aligned on certain boundaries. The reason for this type of extra alignment is if I had a whole stack of these A objects, I don't need to worry about any alignment issues. I can just send them off, make a big array of them, and copy very quickly from one place to another. Otherwise, there would be a lot of fiddling around and trying to figure out where the starting point should be, and copy part of the structure first, and then do the rest. And very complicated business. The extra filler speeds things up. Now, according to my theory, well, first off, what does this mean? There's no B inside. It means if I have an A, I could certainly say A dot sh. They're getting mad at me. Okay. But notice, did you notice that? I can now access directly from A one of these D elements if I want. So basically I've taken over the B name and B is now part of my struct. So essentially A is now the union of A and B, and they're bound together in one thing. This process is called inheritance. Okay, A has inherited B's whatever, inherited, they say from B, but what it's inherited is everything about B, B's properties and data. So whatever you can say about B, you can say about A, right? It contains an array of 6 doubles, right? Well, that's the only property it currently has. But in particular, if I had a function, suppose I had a function. We'll put it here. And let's say that that function took as one of its arguments a B argument. Okay. Now A inherits from B, so it has all the properties of B. So you would think that it should be possible for us to pass our A into B. Now let's see if that's allowed. Now, look at that. Well, we haven't initialized A. 2, 3, 4, 5 is what we had before. Now let's set these D values to something. I'll use one of my magic macros. Is it index and then the array. Let's just, I don't know, multiply by double rand Actually, in order for that round to work, I've got to initialize the common thing, which I added an S round here. I want to fix this problem of forgetting to do that eventually. Okay, so if I cast that to a double, then we're going to get a random thing, but I'd like to make it fractional, so we'll divide by another random number. Okay, and I'd like to multiply this maybe by something to make it clear. Times. Okay, I don't know if you know this POW. That takes a double number and a power. 10 and R. So these will certainly tend to be of increasing value. Let's run up to here and see what we get. Potentially uninitialized now. What's not initialized about A? We did all of the D's. Okay, well let's have a look at A. SH is as expected. D is a bunch of numbers tending to be increasing in value. It turns out this one happened to be bigger than the next one, but eventually the exponential takes over and it gets big. Alright, now the question is, I'm going to be passing A to a foo that takes a B value. Now, A is bigger than B, right? Let's just double check that too. So I want to print %D %B return Alright, we went up to here. We'll check our printout. Okay, same as before. A is that we have the the filler is still there. Now here I am passing something of size A, 56, into foo, which takes something of size 48. Now how is that going to happen? How do you expect that would happen? Well, it certainly can't pass the SH part to B. Now what I'd like to do here is not only would I like to print this out and see that we get exactly the same thing, here's the expression. Current returns. Okay, now I'd like to do that in here. In this case, it's just BC, and just a print. Now this is a copy. It should be a copy. I'm going to call it that because that's what I expect. Okay. And there won't be any A part either. And well, let's just make sure that it actually did do what it's supposed to do. Pass a B in there. And then later we'll look to see how it implements that. Oops. B copy. I want to go to here. So these are the numbers that were generated during the loop. And now we're going to pass this off. First, let's put A in here. Here's A with a whole bunch of, that's the array of doubles. And at the end here is the short. Now that part won't be passed into here. So I'm going to run to this spot and B, I want the address of B copy. Now that's not this address, you'll notice. It's a different address. And I'll drag that into, make another memory window. Which I also don't want there. Just going to put it here. I want to see them side by side. Okay. Make sure we can see everything. Okay, good enough. Now, as you can see, the values are the same, but the addresses are different, so this is definitely a copy. Also, the little bit at the end here, 2, 3, 4, 5, is not included. The last number is 41, just the same as this array. So this printout should be the same. Oops. And indeed it is. Okay? So somehow or other, this function call stripped the A-ness away from A, made a copy of its member, which is not a member anymore, but the part of the structure that is a B, copied just that much of it, and passed that on to foo. And you can sort of probably guess how it would have done that. The address of A itself is of type B, because that's the first thing in the list. It's just as if before I had declared B first. You know, remember with the short from the video you may have skipped, the first thing declared in any structure, if you're not doing this, gives the address of the structure itself. In this case, the first thing declared in this structure is a hidden B here, so the address of this whole structure A is the address of a B. And all it's got to do then is say, okay, well, this thing's a B, I'll copy a B onto the stack and pass it to foo. And that's exactly what it did. You'll also notice, by the way, that this being a copy is not a reference to an array of doubles. This is an actual copy on the stack. You can tell this is stack because it's all starting with 1, 2s. An array of objects copied on the stack. And in fact, if you want to really copy an array from to a function, pass an array, a copy of an array to a function, that's how you do it. You put the array in a struct, and then you pass the struct. Then you won't get any problems with this, reference silliness thing, where it only passes a pointer to your array that somebody can modify. This guy, he can do all he wants with this copy. He can trash all the data inside of B copy, but that's okay. It won't affect my A. My A is safe. There's no access from here to this A. Now I probably have to stop again. Yeah, pretty much I'll stop here. Now this is called single inheritance. This is the simplest case of inheritance. And it's exactly 100% identical to declaring this object here, but omitting the name. Okay. See you next time. See you next time.